The basic idea here is to separate the data motion from the synchronization. So be able to say, move this data, and separate that from this whole issue of when is that data moved. It also separates it from having to describe both ends of the data transfer. So it's called one-sided because the whole description of what gets moved from where and to where is done on one side of that communication. It's done by one of the processes. In MPI, we've maintained sort of the MPI look and feel of this, and you'll see this in a number of ways. But one important part of that is that we don't say all of a sudden you can send data to any arbitrary location in a remote process. Rather, what we do is say that the processes have to say what data they're going to expose for other processes to access. And we'll see that here is sort of described as each part of the process is going to expose part of its memory to other processes, and processes will be able to read and write from that. And an implementation could check for that, at least in a debugging mode. Okay, so we might define this public memory region, and it may be of different sizes and in different places on each node, or it might be in similar places or in the same size on each node. That way, this process here can access the public memory of these other processes, and the source of that data or the destination of the data that it gets from other processes could be in the public memory region, or it could also be in this private memory region. So again, it's one-sided. What you do is you say, here is some data, this public memory region, into which other processes can place data or read data. But on your side, you can use your entire memory as the source of data that you want to place a copy of someplace else, or where you want to get a copy. Okay. And we'll call this a memory window. There's a local window on a process, and all of this memory together we'll call a memory window. Okay. So here's an example where process 0, for example, it might make a request. It might say, I want to get some data from this process, so it has to cause this process to send data here. It may want to put data into process 2. And again, the source and destination of those requests could be all of this memory, both the public and the private. Okay, so to compare this with the two-sided messaging that you've seen before and we've been talking about, we send data and we receive this data. So the process 0 has to explicitly say what it's going to send. Process 1 has to explicitly say what it's going to receive. And then there's some delay in time over which this happens. In the one-sided model, a process either puts data or gets data in another process. That other process doesn't have to make any MPI calls. Now, there's a little asterisk on that statement, as we'll see as I talk about how you know that these things have actually completed. Because remember, I said I separated the data motion from the synchronization or the completion. I did not eliminate the synchronization or completion. I've just separated them. Okay? And I haven't talked about that part of it. So this is just the description of I can put data, I can get data. There's a third thing that I can do, for which there is no direct analog on the two-sided, which is that I can perform an operation at the remote process. So for example, I can add data to locations in the target memory. Okay. So advantages of this are these. So first, you can do multiple transfers with a single synchronization. So each send-receive is there's a handshake there to make sure that the send is completed and the receive is completed. Whereas I can do multiple puts and gets, and then we'll see a single synchronization call that will ensure that they're all complete. And so that reduces, or has the opportunity to reduce the amount of work that the implementation has to do to get all those messages completed. Now, the second thing I've already alluded to this morning is there's no tag matching. So remember, in the send receives, how does the receive know which message it's receiving? So there's information that comes with the message. I've been sent by this process from this communicator with this tag value. So there's 3 things there that I have to check when I'm doing a receive. Okay? And if I posted a bunch of receives, I have to look through that list to find the matching message. There's no concept of that here. You put to a memory location, so there's nothing to think through there. And so that can give you non-trivial savings if that message queue is typically long if you do it with 2-sided message passing. So I would say that tag matching for a couple of items is really not a big deal. Tag matching for 50 or 60 or 100, which does happen in applications, is a big deal. Another thing is that because it's one-sided, I don't have to make sure that everybody has agreed on exactly what's going on. And again, we saw a little bit of that this morning. If I wanted to do my Halo exchange and I wanted to order things so that I was sure that particular communications were happening, it becomes fairly difficult. And in cases where I may not know in advance with whom I'm communicating, it becomes quite difficult. So an example code that we've sometimes used is a simple model of neurons. And when the neuron fires, the big thing about the brain is not the speed of the neurons, which is terrible. It's the breadth of its connections, which is great. So when a neuron fires, you have to deposit little voltages all over the place, but only if the neuron fires. Now, I could just always deposit either 0 or some voltage, but then that would be communicating a huge amount of stuff. So if I only want to communicate when the neuron fires, well, only the owner of the neuron knows that. And so the communication pattern is different every single step. And trying to get every possible destination, every possible connection to the neuron to know what is going on becomes very complicated because it would have to essentially send messages back and forth to find out, did you fire or not? In this case, particularly with that one, with the accumulate, I can do add voltage. And I just use whoever is there. And I don't have to work out this partnership with my destination. So for problems like that, that sort of irregular communication pattern is far, far easier with a one-sided model. Okay. And if you've got the right support, it can be a lot faster. So in particular, systems with, there were some very large shared memory systems where your shared memory program might not have been as fast as you wanted because of all sorts of locality issues. But by using MPI, you would get nice locality for the performance, but all of the, but communication between the processes could be done with the hardware helping to support these sorts of one-sided operations. On those machines, this was actually quite fast. It can be implemented so that it is fast even on modern distributed memory machines. And in fact, the best paper at SC13 last year showed an implementation on the Cray. And again, Torsten led that effort, where the one-sided was both fast and in fact comparable in performance to Core, Fortran, and UPC. So there are existence proofs where this is fast, but it's also not easy. So keep that in mind. Yeah, so I think I just said all of this. Yes. Okay. So I hope you're now interested in this. What I'm going to do is talk about how we do this. So first, I talk a little bit about how we create how we create the memory. We don't really create the memory. We mark the memory as available for these operations, how we do these updates, then how we do the synchronization. And I want to say a little bit about the memory model, which is always the sort of here be dragons sort of problem. When you start looking at multiple processes accessing the same memory locations, all sorts of very subtle and dangerous issues come up. And it's one of the reasons why shared memory programming is not as popular among people who have to do work as one might think, because there's a lot of things that go wrong. It's also the reason why most of our laptops crash occasionally, because they've been programmed with effectively in a shared memory model without enough rigor. Okay. So how do we do this memory? So the first thing is pretty much you can use any memory you want. And again, there's an asterisk on this. But for the example, particularly for the example that is in the MLife code, memory can be anywhere. So you can use malloc to create the memory. You can use a declaration. I could have said double precision x of 100 to get that memory. You do have to make an explicit MPI call to declare that memory region as exposed to other processes. And that's then a window. In MPI 2, there was exactly one call to do this, called MPI win create, to create the window. In MPI 3, there are 4 calls to do different varieties of this, including ones that return the memory rather than accepting the memory. But once you do this, once you create this memory region, that memory is available to all of the processes that participated in that creation. So window creation is like communicator creation. It is a collective operation that the processes have to take part in. And that allows them to know about each other's memory and to have necessary communication channels. And one of the things, so you might ask, well, what if I don't know the memory at the time I create the window? Well, one of the things that MPI 3 added was a way to deal with that. So let me just defer that for a moment. Okay. So then we've got this situation. So here, for example, I'd say this is each of these processes. The yellow is all of their memory. Let me let the gray here be the memory that I've given to MPI win create. That becomes, the union of these is the window object. Each of these is the window. And a get can go, has to go from the window, but can go to anywhere in memory. And a put, again, can come from anywhere in memory, but must go into the window. And now we can build this up. MPI win create is, as I mentioned, what we do to expose that memory. Again, it's collective. It creates a window object. So out of this call comes a thing like a communicator. It's called a window. It's MPI underscore win in C. It's an integer type in the old Fortran binding, and it's an MPI underscore win in the Fortran 08 binding. And you use that in all of the one-sided communication calls, essentially the same way as you would use a communicator in a send and receive. As with all other MPI objects, if you have a create, you have a free. And this deallocates the window object. Again, it's a collective call. Everybody needs to free it collectively, just like free a communicator. And then the core routines, these are the ones that came with MPI 2, are put, get, and accumulate. And as I think Rusty mentioned, and I will say, I lobbied for them to be called I put, I get, and I accumulate because they are all non-blocking. In fact, there is at least one published paper that came out shortly after MPI 2 was released where they got that wrong. And the reviewers didn't catch it. So I think that's the proof that they should have been called I put, and I get, and I accumulate. But they weren't, so you just have to remember they're non-blocking. There is no blocking version of these. and they're non-blocking in the MPI sense. So that means they initiate the communication. You can't reuse the buffers in the case of a put. You can't access the buffer in the case of a get until they have been completed. So we need something similar to a wait all, and that's going to be the synchronization, which I'll talk about a little later. The benefit of making these non-blocking, well, this morning, remember I mentioned in doing that mesh example that if I had replaced the iSends and iReceives with a mem copy, I would have the same, potentially the same performance trouble because that mem copy would block and would force extra synchronization of the code. Because these are non-blocking, again, with the appropriate implementation, you potentially don't have that problem, that it's possible for the implementation to move from target to target, one-sided communication to one-sided communication to make sure these things are able to keep using the network. Okay. So as I mentioned, MPI 1 or MPI 2 had one way to create windows, and MPI 3 added 3 more. So the original one was MPI Win Create. You use that one if you have a buffer, some memory that you want to make available. I should say you can only make a contiguous block of bytes available. So for example, you can't take a submatrix inside a multidimensional array and say just this submatrix. You have to make a contiguous block visible. In many cases, a better routine, unless you are using the older Fortran binding, is MPI Win Allocate. So MPI Win Allocate will return memory to you. So why is this better? There's a couple of reasons. One is that it may be able to do what's called symmetric allocation. How many people have heard of symmetric allocation? Okay, so think about what you have to do. I want to put data at a remote target. And by put, remember, one-sided, the process doing the put has to provide all the information. Well, some of that information is where. Where does the data go? Okay. So as we'll see, MPI actually makes it a little easier in the sense that where is defined as an offset from the beginning of that public memory. But if I'm implementing, now look underneath in the implementation wants to take the data and plop it into an address. So where is that address? Well, that address is going to be the offset that you gave it when you say put the data, plus the starting address in the destination memory of that block of window memory. Well, symmetric allocation is one where everybody allocates their memory at the same spot in their address space. Well, you can't always do this, but if you can, it means that everybody instantly knows where everybody else's memory starts without having to do anything. In the case of MPI Win Create, everybody's block of memory might start in a different location. And what if there are 1 million processes? That means that you have to be able to find the starting locations of 1 million different pieces. In the case of symmetric allocation, I just need that one number. And this is, in fact, a critical feature of the way you implement things like co-array Fortran, because it takes advantage of that my address happens to be the same as the address of that object for you, because they all have the same base locations. Yeah?
What would be the overhead, the time of doing a MPI Win Allocate call if there are 1 million processes? And that overhead, because it has to pretty much guarantee that, and talk to all 1 million that, is this spot available?
So there's, so it's an implementation issue. So first of all, I will say it doesn't guarantee symmetric allocation, right? It doesn't guarantee it. So one of the things it can do is it could do effectively an all reduce of available memory locations to find out if there was a good spot available. So that's the cost of an all reduce. So 6 to 12 microseconds on Mira. And then everybody uses the same logic. So they make the same decision, and then you go. So it's not that bad. It's actually better than what you do if you decide that I'm going to have to get the different addresses from different places, because then either you have to do an all-to-all, which is what a lot of the implementations do right now, so they've got the data, or you have to set up a mechanism by which you acquire it on demand, which adds extra complexity. So you may have to do that at the million process thing. So, but those are all implementation details underneath. They will impact the performance. So then there's MPI Win Create Dynamic. That's what you use if you don't have the buffer yet. So this is the MPI Win Create Dynamic is what you use if, for example, you're doing adaptive mesh refinement and you're dynamically creating grids. This is the one that would allow you to add a grid to a memory window. And then MPI Win Allocate Shared is a special one that allows you to get memory that is, in fact, shared, which once you've got it, instead of using MPI put and MPI get, you can, in fact, use regular loads and store operations. So and I'll say a little bit more about this. But this is a special thing that allows an MPI implementation to say, you've got a bunch of processes that are on the same node. And that node has shared memory hardware support. And so rather than keep you from that, I'm going to let you have access to it. It doesn't guarantee that I can get a shared memory window across all possible processes. So there's no sort of virtual shared memory support here. But there is a way for you to set things up so that MPI processes that are on, again, say the same node can share memory. Okay. Sorry? Yes?
Is that more efficient than, for example, to use this approach instead of OpenMP? Or?
It might be. The reason for that has to do with locality. So OpenMP, one of the targets of OpenMP was to make it easier to program in parallel. And they made a decision to keep it easy by keeping you from worrying about locality, because locality is what causes a lot of the trouble. And they're absolutely right. Thinking about locality is harder. Unfortunately, thinking about locality is how you get performance. And so the reason why this might be better than OpenMP is that MPI sort of forces a locality model. It's also a locality model that the operating system tends to enforce. And one of the reasons for that is when you think about the locality model for threads, the locality model you want to use for threads that are used in a web server that's a different kind of locality model than you want to use for a sweep over a grid. So the operating systems tend to optimize the use of threads for the other model, because that's where all the money is, as opposed to our model. So the upside is, yes, you might be able to get better performance with it because you've got more control. The downside is that you don't get anything else that comes with OpenMP. Right? So you'd have to do everything yourself. So again, it's one of those things where your mileage may vary. Okay. No question. Yeah.
For the create dynamic, you said that, yeah, you don't have the buffer yet, but you are going to allocate it in the future. Now, do you still have to decide about the size of the memory that you like to allocate in the future? Is sort of like just reserve and allocate later, or no?
So it's completely flexible. So once you said I wanted to create this window to which I'm going to dynamically attach memory, each process can attach memory of any size at any time independently. Okay, so enough beating around the bush. This is what MPI win create looks like. It has just a few arguments here. So the first two describe the block of memory. So the base address and the number of bytes. And it really is the number of bytes. That's these two. This is a displacement unit. So remember I said that puts and gets and so forth will be, you'll indicate the location that you're accessing as an offset into this window. And so again, you're not going to be doing puts and gets to an address. You don't have to know what the address is of the target. You just need to know where in that region you want to access the offset. But the question is, how do I scale that offset? Is that offset scaled by bytes? Is it offset scaled by ints, by double precision quantities? That's how you set the displacement unit. So the displacement unit is, what's that unit of offset? If you're using this block of memory on which you're going to do one-sided operations, as, for example, a big array of integers, then that displacement unit should be the size of an integer, because then your offsets are essentially enumerating the count for that integer. If it's more complicated, then you use a displacement value of 1, and then all the offset units are bytes. The next parameter is an MPI info. So MPI info was another thing that was added in MPI 2 to provide a way to give the MPI implementation some additional information in a way that was easily extensible. So an info is a collection of key value pairs, which are all strings. So I can say I have a string name, and it has a string value, and my info can have a whole bunch of those. And I can use those, for example, to tell MPI when create that I'm only going to use one particular synchronization model that might be a little more efficient than the general case. And we'll say something about that a little later. Okay. Then the last input variable is the communicator. So as I said, this is a collective operation. It is collective over a communicator. And that's it. And out of this comes a new object, the MPI win object. Again, just like if you did a com split and you would get a new communicator, here we do a win create and we get a new MPI win. Okay. And so here is how you might create it. This is going to set up, each process is going to have an array of 1,000 ints. So we allocate this array. It's regular memory, so use it the way you use normal regular memory. We do MPI win create, so we pass it the memory location, the size in bytes, which is 1,000 times size of int here. The displacement unit, size of int, so that means that my offsets will all be in units of ints. If I don't have any info, there's a special info object, MPI info null, which is I think, in fact, we probably should have called this the empty info instead of null info, because usually null handles are invalid inputs to MPI calls. But in this case, this one's allowed. Use com world here, and I get a new win. Right? Then I'll be able to do things. When I'm done with this, I free it. For C users, of course, again, you pass the address of this because it's going to set win to MPI win null at exit, so that then if you mistakenly used it again, you will get an error. As I mentioned, there's this MPI win allocate, which in many cases may be a better choice. And what does it look like? It's about the same thing, except instead of passing it an address, it returns an address. Note, this is one of these places where it says void star. And you're saying, well, how can it return an address? This is a C idiom. In fact, this argument is treated as the address of a a void star pointer. So it's treated as if it's void star star. But the weirdnesses in C means that I can pass the address of a pointer to this and it won't complain. If I pass in, if I made this star star, I would have to cast the pointer to be a void pointer first. Right, so this is just the fact that this has a single asterisk or single indirect in the definition is an artifact of the idiom. Okay, and so it returns a pointer to the memory that was allocated of this size, as well as the window. Okay, and so in this case, we eliminate the A equals malloc. We pass the size, and we are returned. So this is the address of the pointer to ints. We also get back the window object. Creating a dynamic one is pretty much the same. There's a little bit of extra stuff here, but there's no buffer that gets passed in the beginning. Later, memory is attached to it. It can be detached, and it looks like this. So there's the info again. We can pass it in. I can now create some private memory. And here I do an attach. So I take my dynamic window, and I attach memory of a certain size in bytes. The way this program is written, everybody in CommWorld is doing this. But in fact, I could have had some, if rank equals 12, do this. Each of those is independent. Right? It doesn't have to be the same number, or doesn't have to be the same sizes or anything. When this routine returns, that memory is now accessible to one-sided operations from the other processes. Now, of course, they don't know that. So you'll have to have some other mechanism to let them know that it's there and what its address is. Because in this case, in the case of the dynamic windows, the offsets are basically the addresses. Okay. Once you're, when you're done with this, you can detach it. So again, you take the window and pass it the pointer. That detaches that memory. That means that it's no longer publicly visible. It should also have to be, you also can free it. You have to free it separately. Okay, so those are the creation routines. For data movement, MPI2 had get, put, and accumulate. MPI3 added get, accumulate, compare, and swap, fetch, and all. These are versions of accumulate. By that, I mean they perform an operation at the target process, which is what accumulate does. But they added something which was missing, which is that they also return values. So maybe the easiest one to explain is fetch and op. So if I wanted to maintain a remote counter, then what and I want to be able to update that counter, then what I need to do is get the current value of that counter and then add 1 to it. I can't do that with an accumulate and a get, or a get and an accumulate, because remember, they're non-blocking. So if I called MPI get, MPI accumulate, I don't even know which order those are going to happen in. There's another rule that says I can't even do that anyway, because it's not clear what it means. By combining these operations, I can say, fetch and op says, fetch the value and perform this operation and do it atomically, so without allowing other processes to break in. So in particular, this means that if multiple processes are doing a fetch and op, you won't have the situation where they both fetch the same value and then add, each of them adds 1 to it. So if process 0 and process 1 are doing fetch and op, maybe process 1 wins the race. It gets the value 0, increments the counter to 1. Process 0 then gets the 1 and increments the counter to 2. And again, you can't do that with separate gets and accumulates. What get accumulate is, why we have fetch and op and get accumulate. Get accumulate is the general case. Fetch and op is shorter, intended if you're just doing one data element. And then finally, compare and swap. How many people know about compare and swap? Okay, compare and swap is a very powerful operation which can be used to build some interesting algorithms when you're sharing memory. Some hardware provide a compare and swap instruction. Other hardware provides instructions out of which you can build compare and swap. There are some subtle things to worry about when you use compare and swap, but it does give you a very nice way to implement some algorithms where multiple processes are updating the same data structures. Okay, so get looks like this. It has a lot of arguments, but it really is pretty simple. So, and it's been broken down this way to make that obvious. So it has, what am I trying to get to? So where is the data going to arrive? Where am I going to put it when I get it? Where is it coming from? What process? Where in that process's memory window? And what of these window objects is it in? Right? So if I took all the arguments in send and receive, it would be at least as long as this, right? Because there would be, so for the receive, there would be, this is the receive, specify the receive buffer. This is the send, because that's going to be the data that I'm going to get. And this is the rank of the other process and the communication context. Okay. Now, note that these all have counts and data types. So I said that these things all look like, they had the look and feel of MPI. That meant that they had data types. So these data types don't have to be simple data types. They don't have to be just MPI double or MPI integer. They can be a vector data type. They can be a struct data type. So I can use this to grab non-contiguous memory. And I can have 12 structs or something. The first argument for these routines is my local buffer. So that's the origin process, the process that's making the call. That's why this is called origin. And so this will be an address. The target, again, is not an address. It's a offset or a displacement from the beginning of the remote memory window. And so that's why this is target disp instead of target adder. Okay, so that's what this does. Oh, and then just as in a send-receive pair, the data types don't have to be the type maps don't have to be the same. So I can have contiguous on one side and vector on the other side. The same is true here. Put is basically exactly the same thing, except data moves in the other direction. So data moves from here to here, but the arguments are exactly the same. Okay. Accumulate is almost the same, except there's one other argument, which is an MPI op. But it yes?
I was just wondering how you knew the origin data type.
Oh, well, you pick that. Okay, so let me go back here. So these data types are just describing the layout in memory that I'm going to be using. So for example, in the case where I've allocated this big array of integers, the most common use will be to say MPI int or MPI integer in Fortran, and the same thing here, and I'm just moving a contiguous block of integers from one place to the other. But I could have I could say take an MPI type vector of integers with some stride. And that would allow me to take, for example, a row in Fortran, and if I put it to just an MPI integer here, it would be putting it into a column if I viewed it as a matrix. But I get to make all those decisions. The thing about one-sided is everything is on, it has to be known by the origin. So and maybe seeing some of the examples will answer your question.
Yeah, so the data types that the origin has created are known to all of the processes?
No, so this is really, really one-sided. So maybe I should say something about how this might be implemented. So the origin is the process that's calling this. Okay, so it knows the origin data type. So what happens with this target data type? So the target data type is not a data type on the target. It is the data type on the origin that is to be applied at the target. Okay. Now, that means that the implementation may, in fact, have to send a description of that data type to the target process. But yeah, everything here is described, is known at the origin and is described in terms of the origin. Okay. Oh, that's a very good question. Okay. Let's see, I'm going to finish here. Oh yeah, so you can only use predefined ops, so MPI sum, MPI product, MPI min. You can't use a user-defined operation. Why is that? Well, in a perfect world, you should be able to do that. But the concern with the forum and the vendors was that what I'd really like to do with accumulate is the origin causes something to happen at the target, and maybe the operation happens in the network card. So the network card has a little floating point unit or something, and it does stuff. If it's a user-defined operation, it means I have to send executable code over to the target. And nobody really wanted to contemplate that. There is a name for that sort of operation. There's been a lot of research in things called active messages. There's still interest in the MPI forum in that, but we wanted to stay away from that. I think that was the right decision, but it does mean that there is this limitation. Okay.
I mean, because if the user creates MPI off, then it's committed by the user at the time of creation. So at that time, I mean, it's a one-time cost, right?
Well, it's committed at the origin, but an accumulate operation happens at the target.
Exactly, but MPI, at the time of commit, MPI can send it to everybody.
It could, but part of the feeling was that what you wanted was the accumulates to be as fast as possible, the puts to be as fast as possible. And so what you really wanted was them to not involve the CPU at the target at all. Right? And if I'm just doing a put, and I've got RDMA hardware, this is the case now. Right? So if I know the address, I can just do the put. And the CPU doesn't even know anything has happened, which may or may not be good. But it doesn't get involved at all. And the idea was that maybe the network card would also be able to do, at least if the number of operations was bounded, maybe they would put these things into the network hardware, again, keeping the CPU uninvolved. It's a couple other things, too, because MPI was designed to handle heterogeneous systems. So it's possible that object code that I have on my target, on my origin, would not run on the target and would have to be translated. And that would have been a legitimate MPI program. And at the time this was designed, that was not unreasonable. In some sense, it's still not unreasonable because there still are multiple instruction sets that are popular. So we also added a new operation, which is called MPI replace. And what it does, it's an op. It takes two values and throws one of them away and puts in the new one. So it effectively gives you a put. The reason it's there is that one of the things I haven't talked about is what happens if multiple people are trying to put or get to the same locations. And the answer is going to be sometimes you're allowed and sometimes you're not. This is how using replace is how you can be allowed to do that. Get accumulate is like get, but again with an op. So you do the get, you perform the op. And again, it has the same sorts of benefits. And the counterpart to replace is MPI no op. And basically, that's saying that instead of plopping data at the target, I am reading the data, but with a rule that allows me to do this with multiple people touching the same data. Okay. So, yes?
So the get or put with an opt,
Yeah.
aside from maybe convenience, what was the benefit on this?
So, in fact, let me go to this. One of the questions is, what happens if, say I'm putting 10 ints into the memory, and I'm getting 5. And the 5 that I'm getting are in the middle of the 10 that I'm putting. What does that mean? But they're non-blocking. And what if what I'm putting is a double complex? So I'm putting 10 double complex values. And I get 5 double complex values. Well, is it possible that I might get the real part of the old value and the imaginary part of the new value? It'd be kind of painful. You'd like to say, these things will always work right? The problem is that if I say that, I may have also sort of implicitly told you it's going to be slow. And all of the people who are looking, why would you ever do overlapping accesses are going, why are you making my code slow? So what MPI has done is it provided 2 ways to get the data. There's one way that's really good and fast if you promise never to do stuff like that. And so it doesn't have to worry about making sure that every object gets dropped in atomically so nobody can get some bytes of the new one and other bytes of the old one. And that's what you use put and get for. So in principle, they can be the fastest. They might be able to use the hardware because the hardware that you have for these remote operations tends to be pretty loose. And so it doesn't have very many guarantees on what it does. Mostly it's moving bytes. So it doesn't know, for example, you have to move this object as 16-byte atomic units, which is what a double complex would require, or 32-byte objects, which would be a long double complex, for example. Most of those things just move bytes. But sometimes this is important, right? Sometimes you really do need to read those 5 values and be able to put to them. So you can do that, but you have to use the accumulate routines. And the put that behaves well that way is accumulate with MPI replace. And the get that behaves that way is get accumulate with MPI no op. So it's basically a different way to name, sort of like an atomic put and an atomic get. And it just meant that we didn't have an extra, yet more routines, which people seem to find objectionable. Yeah?
Just a little unclear as to what the target displacement means. Is that the displacement from the start of the remote memory window in the target?
Yes. Yep. Yeah, so you don't have to know exactly where that window is. You just need to, you have that collective creation. You need to know that it exists. And so that means that your computations can be based on knowing how you've described your data structure without knowing their address. In fact, without even knowing their addressing system, right? Because again, this model would work even if you had the right kind of implementation. And I know of no implementations for which the following is true. But In principle, you could do an implementation where you had some nodes with 4-byte addresses and some nodes with 8-byte addresses, and this would all work, right? And the nodes with 4-byte addresses wouldn't have to find some way to do 8-byte arithmetic. Okay. Similarly to this, the reason I put the slide up for the question you asked about the get accumulates and puts and whatnot is that related to this is, are these operations ordered? And again, it comes down to some people need them to be ordered and some people don't. And ordering is not cheap. Modern networks tend to inject messages into the network and then they fly around and eventually land. You might inject a message and it flies around and it gets, it's like there's a storm at Chicago and it gets rerouted off to Anchorage. And then another message gets sent a little later and the storm's gone. If those were your puts, the puts started in one order, they arrived in a different order. Maybe you're fine with that. Right? So again, I don't want to make everybody slow just to deliver a certain view that some people might need. In MPI 2, nothing was ordered. So suck it up, you only get this unordered. A lot of people complain that there were some algorithms, some things that they wanted to do where it was important to provide particular order. So in MPI 3, it changed a little bit. So puts and gets are still unordered. So again, you can sort of think of the puts and gets as the fastest, but with restrictions, sorts of operations. Accumulates are ordered by default, but you can use that MPI info to control that. So if you don't need your accumulates to be ordered, you can, in fact, request that as well. But by default, they're ordered. And then again, if you need an ordered put or an ordered get, you use the accumulate with replace or the get accumulate with no op. And so that way, we've been able to cater to a broad variety of needs with a small set of routines. Okay. I mentioned the compare and swap and the fetch and op. Fetch and op in particular was set up after long discussions with people who were designing hardware so that we hope that fetch and op will in fact be implemented in the network hardware. There's no reason why not. There's already been examples in the past where some systems have implemented effectively part of fetch and op sort of operations in their network hardware, at least for limited sets of data types. So you can imagine a network controller implementing this for like integer data types and then maybe punting floating point off to the CPU. Okay. Yeah.
I was just going to comment, I think BGQ is MPI 2 gives people.
Yeah. Yeah, so the MPI-CH has the MPI 3 implemented, so you can play with MPI 3 on your laptop. The MPI 3 code is slowly rolling out to the vendors that use it to build their systems. So maybe even not so much that slowly. So if you're looking at designing code now, I think it's reasonable to look at the MPI 3 features. Okay. Okay, so we've talked about the data motion. I've still left you in suspense about how you know that the data is there. And MPI provides effectively 3 synchronization models with a couple of variations. So there are a couple of questions that you have to look at. So when you do a put, there's the question of when is that put done? In other words, in the MPI sense of a non-blocking routine, the non-blocking routine is done when I can reuse the buffer that I passed into it. Right? So if I do a put and I passed in a buffer, I can't touch that buffer. I can't change it until something happens. So I need to know that. More interesting, of course, is a get. When can I use the data that comes with the get? I need to complete that operation. And you can sort of think of these as sort of an epoch in which these operations happen. And there are these sort of three types that have sort of in two groups. So the first group are what are called active target. And active target require the processes effectively collectively to decide when any RMA operations that may have happened can start and when they can complete. So fence is the easiest one. Fence is a collective operation. So you pass fence the window that you're performing an RMA on. And when fence, you should have a fence at the beginning and a fence at the end. The fence at the end, when it returns, your RMA operations have all completed. So it's a single call, completes whatever RMA operations were there. And there's no sort of notion of there's not a separate call for origin and target. It's everyone in the group of the processes that form the window have to call it. So it's collective over that. It's another one that's called post-start complete wait, which is the awkward way of saying that, well, I've got all these processes doing this, but I just want to describe the processes with which I've performed RMA operations. And in principle, that could be implemented in a slightly more scalable way because I don't need to do what is effectively a barrier synchronization across the entire machine. I just need to coordinate with processes that I've either been the origin of RMA operations with or the target of RMA operations with. And that's why there are four names here. You call two of the names are to start the fact that you are going to originate RMA operations, and two are start and end, and you're going to originate, and two of them are that you're going to start and end being available to be the target of RMA operations. Okay. And then the final one is called passive target, and this is the only one that is really truly one-sided in the sense that the only MPI calls that need to be made are made by the origin process. So this is the one that you use if you want a process to go and get data from another process without that other process making any kind of MPI call at all. In the active cases, processes have to at least make the synchronization calls. Okay. There's MPI3 gives you some finer control over the completion of the RMA operations in this passive target mode. It allows you to forcibly complete routines while you're in this sort of epoch of I've done a lock, I do some RMA operations, I can do a flush to flush them all out and get them completed, and then do some more. Okay. So what does fence look like? Sort of looks like this. It's a very collective synchronization model. You should, semantically, it's like a barrier. Now, whether or not the implementation actually does a barrier depends on what the implementation wants to do. But from the point of view of looking at your code, you can think of it as I do this barrier-like operation, then processes can do any number of RMA operations, and then at some point, everyone again does a fence. And so in this case, this process did one RMA operation. This process did none, but it did make the fence call on both sort of the beginning and the end. And at the end of this fence call, this get is complete. You know, I don't know that it's complete until this fence returns. And similarly, I mean, in this period, the target process should not be updating its window because this get is, you know, God knows what it'll get if you update that window that way. Okay. The post-start complete wait is fairly similar in the sense that I can start issuing RMA operations, and then I can have those operations complete. And on the target, I post my window so that it can be accessed, and then I wait for those accesses to complete. So, and it's like fence, but it's a little weaker. The lock-unlock, as I mentioned, is the only one where only one process makes any calls at all. So you do a lock, you do gets and unlocks. Now, I should say, we always make a mistake in MPI. I'll have to figure out what we've done wrong in MPI 3. We've always misnamed something. So in MPI 1, the extent, the data type, that's the stride. We should have just called it a stride. Would make things so much easier. In MPI 2, it was lock, because this is not a lock, right? So lock in the sense of mutual exclusion, this is not a lock. What this is this lock is really begin access, and this unlock is end access. It does not have the semantics of a lock. It does not have any kind of mutual exclusion. In fact, one implementation, so for example, let me say I was going to do a put. Let's say I was going to do a put of one word, right, which I might want to do. Well, if this really was a lock, then I would have to go get the lock, and I'd probably have to get the lock at the target. So I'd have to send a message, get a return saying, yep, you got it. Then I could send my data. And then I do the unlock, which would be send a message saying, OK, you can unlock now. And then, in fact, I get back a message saying, yes, you've unlocked. So that would be 5 messages just to send one word. And I said, this is going to be faster? Well, because of the semantics of this, that the lock is really a begin and an unlock is an end, it's completely valid for the implementation to see the lock and say, ah, good, it's a begin, and return. And then it sees a put and says, oh, this is a short put. I'm going to hold on to this for a moment and see if there's anything more I want to do with this, because this is a huge amount of effort to dispatch this put without doing anything else. And then the next thing it gets is an unlock. It says, ah, this is great. And what it does is it puts them all together and sends a, go put this word in, and you're done. Now I'm down to one network transaction. Right? In fact, this is what MPICH does. So it's important to bear in mind that this is really a begin and this is really an end. And this is why it's also called passive, because the target is passive. It makes no MPI RMA calls to complete. The other ones are called active because all the processes are involved, even if they're not issuing RMA communication calls, they're involved in the synchronization. Okay, yeah?
In this case of passive, how does the ordering, I mean, it has to matter. I mean, if 4 processes are trying to write and read from a remote location, how do we deal with that?
So there's a locked, let me go to this one. There's a lock type, which can either be shared or exclusive. In the exclusive case, it says that only one process at a time can perform the sequence of operations between the begin and the end. Okay, so if I was doing this one little atomic operation, when it arrived, it would have to see whether it could get the exclusive access before it was performed. So it can't just sort of arrive there. But then it could happen atomically. If instead it was, I did a lock and then I did 38 different RMA operations and then an unlock, the exclusive would say that I'm not going to get to do those until I can do them all with nobody else accessing the memory window. In the shared case, other processes can access as long as everybody is saying shared. And as long as they're not making overlapping puts and gets. Right? So if there's a danger that you might be putting data that somebody else might be getting, you need to use exclusive.
It's the programmer's responsibility.
It's the programmer's responsibility. This is a very low-level interface. Okay. So you do a lock, you give it this lock type, you lock a particular target rank on a particular window. And then there's an assert, which is a compromise. This is to provide a little more information that the implementation can use to optimize things. Well, I said, we've got WinCreate, and it had this info thing, which is really great. Right? But it's a bunch of strings that I have to read. So in the MPI design, we decided that while info might be fine when I'm doing a heavyweight operation like creating a window or communicators in some types, or I'm spawning processes, it's really too heavyweight to be used on operations that I might be doing frequently and that need to be fast. So instead, as a sort of special case here, there is an int argument, and there are some predefined values for that, which allow you to say a little bit more about how you're using the lock. So it's less general than an info, but it's also cheaper. And a value of 0 is always correct. Right? And in fact, that's what I would recommend. So, values of assert here are optimizations, and I would not do any premature optimization. Okay. Yes, okay. So that's that. So when should you use the passive mode versus the active mode? The passive mode really fits when processes are operating independently and need to access the data, and if the implementation can give you direct support. And as I mentioned, there are some examples. InfiniBand provides some of this support. So there are some commodity networks that provide this support. High-end proprietary networks, both BlueJeans and the Crays, for example, provide some of this support, so you can get that. The passive mode does have a challenge, which is that it is passive. There is no MPI call at the destination that can help move things along. And so that means implementations have either been wrong, so that sometimes things don't happen until some kind of MPI call happens at the target. And so sometimes what that means is that, again, you might find that by putting in calls to MPI iProbe, just various places, might cause things to move ahead. Some implementations have an option to create a separate thread that might run. Then that can service any requests that come over, but it has the extra overhead. First of all, it has to run somewhere. And so that's wherever it's running, you aren't, or your computation code is not running. And once you've got a separate thread that's doing that sort of communication, the whole implementation has to be careful to make sure that the different threads inside of itself keep things consistent. And there is overhead with that as well. Okay. So there are all these nice operations. There are some good opportunities here. I think you will see better and better performance from the one-sided operations. I will say that it's had a rocky history. When it first came out with MPI 2, most of the systems made in this country did not do RMA very well. The fastest machine in the world at the time was the Japanese Earth simulator, and it was great. It had a wonderful implementation of MPI one-sided. They had really taken advantage of all of the possibilities here. Now it's, the Japanese machines are still very good at the one-sided, but their market share has become quite small. And the other systems have gotten much better. So, for example, the IBM system here is significantly better on its one-sided support than the systems of about 10 years ago in terms relative to the two-sided. But as you'll see, not necessarily better. As I mentioned, an experimental version for the Cray performed very, very well, but the production version's not as fast as that. But that also should tell you something, is that we're now close. So we know how to get really good performance with the one-sided operations, and I think that over the next couple of years, these will become very fast within MPI. Okay, any other questions? Yes?
I have a question. When you talk about MPI implementation, and this machine implements it well, and who are the people who are responsible for having that good implementation? Is it the people who designed the cluster, like IBM? Is it like who's writing the software? Who do I complain to?
Well, you should complain to the vendor. So whoever sold you the system bears the ultimate responsibility. Now, the MPI is a very interesting object because the infrastructure that most people are built on is from, at this point, 2 public implementations. So MPI-CH and OpenMPI. Almost every implementation of MPI that's running today is a derivative of one of those. But it's a derivative. So I know MPI-CH much better, of course. It was designed to allow the vendor to plug high-performance stuff into it. Right? So if you're not getting high performance, it may be their fault because they've failed to plug in the right high-performance stuff. Sometimes it's our fault because the performance problem is above that layer and it's something we did wrong. And the vendor is not shy about letting us know about that. So again, complain to the vendor. And in some cases, it's a mismatch between what the hardware can do and what the standard does. So for example, let me think about this. So for these one-sided operations, there are certain rules that they all have to follow. And if your hardware implements 90% of those, but can't catch that last 10%, you might not be able to use the hardware at all. Because in order to guarantee that you never make a mistake, you might not ever be able to use some feature, or you may only be able to use it after a lot of extra work. So for example, we were just talking about this exclusive access. So if my hardware allows me to put data into a particular memory location, but that's it. It doesn't give me any way to keep multiple processes from dumping memory in the same locations. I might not be able to use that, at least directly. It might be that before I can tell it, go ahead and plop that data down, I have to exchange some messages to do some coordination, and that adds extra overhead. Well, the hardware isn't quite right. And so again, the vendor. Right? But at this point, the vendors are often system integrators. What that means is that what they put together, they've gotten from multiple places. Okay, almost all of them do that. Cray, for example, doesn't make processors anymore. There was a time when they did. So, if your processor is misbehaving, you don't complain to AMD or Intel. You complain to Cray, who then complains to Intel or AMD. Same thing here. Complain to your vendor, and if it's the fault, if it's the underlying implementation's fault, believe me, they will get back to them. Yeah.
When you allocate the window, its size must be as large as the largest boot that you will perform.
Well, that memory region that you allocate is all of the memory that you're going to allow other processes to access. Right? There's an asymmetry here. I could allocate a memory window and give it as the buffer size 0 for my process. And some other process says 1,000 words, because the sizes will all be different. I can still put 1,000 words into that window, but nobody can either put or get anything from me because I said 0. So I want to say it that way. And then The same thing is, it would be the largest put starting with a displacement of 0. Would also be that, so not the largest put, but a largest put with a displacement of 0. Because really what I'm doing is I've got my memory space and I'm saying this piece here on, could be the target of RMA operations from the other processes in the group that form this. And just that piece. And trying to access outside of that piece, either with puts or gets, is an incorrect program. It's like a out-of-bounds array access. Okay? So I've been talking about this RMA stuff. You can go ahead and give it a try and look at the performance with the fence synchronization. And you could try to use the passive target synchronization. And I will warn you, it's a little trickier than it might look at the beginning. So you should think about why it's trickier. One thing to remember is, when do I know that data is updated? The send and receive is pretty easy. When my receive completes, I know that things are done. How do I know that things are done if if somebody's doing puts? Okay. Or how do I know that I can start a get? Okay. So give those a try. Don't be surprised if RMA is slower than the point-to-points, unless you're running on a particular machine somewhere else. That's probably what you will find. But give it a try anyway.